This next session is about coherent optics and holography, which is one of my favorite topics. Super excited to hear this. So the first talk is Florian Willimitzer from University of Arizona.
Yeah, so thank you very much for the introduction, and hello everybody. So let me say it's like super nice to be here back again in this very nice, great ICCP community. Thank you again to all organizers for this invitation. So again, my name is Florian Willimitzer. I'm an associate professor at the College of Optical Sciences at the University of Arizona, where I direct the computational 3D imaging and measurement lab. And as the name says, our group is working in computational imaging. And one of the things that we are especially interested in our work is the question, how can we utilize fundamental physical and information theoretical limits to invent, develop, and build better computational optics and better computational imaging systems. So what you see here, this is our current group and our present and past academic and industry collaborators. And here you see kind of an overview of our current research project. So summarized on a high level, what we do in many of these projects is we take classical high accuracy optical imaging techniques, for example, from optical 3D metrology, and then we combine them with additional encoding strategies and smart algorithms. And this allows us in the end to push these high accuracy principles into novel application regimes. And before we start with today's main topic, I will quickly highlight a few of these other research tracks, because I think they are also interesting for this community. And at the same time, this also gives you kind of a more complete picture about what we are doing. So feel free to snap here a photo and look at the related papers here on the bottom. So the first thing I would like to highlight is our eye tracking research, which uses a technique that comes from optical 3D metrology. It's called deflectometry. And we do basically computational deflectometry, and we use that to sample the eye surface with high density. And this allows us in the end to evaluate the gaze direction of the eye with high accuracy. So this was published last year in Nature Communications. And then we have a project that is also interesting maybe for this community on event-based structured light. Here our technique is able to measure these scenes with mixed reflectance properties, as you can see here. And we are able to do this with high 3D accuracy below 600 microns. This was just published a few weeks ago. And then the third thing that I would like to highlight is a series of multimodal approaches where we fuse polarimetric information with deflectometric information. And we can use that, for example, to remove ambiguities and to significantly increase the normal map error. In this case, from like wide over 5 degrees from shape from polarization to only 0.6 degrees in this specific work. So these were these kind of, elevator pitches that I wanted to say at the beginning and that I cannot discuss in greater detail. But I'm happy to come back and discuss them at future ICCPs. But these teasers hopefully already showed you a little bit that, in general, our research can be applied to multiple fields. And this includes industrial inspection, this includes medical imaging, this also includes robotics, automotive, cultural heritage, AR, VR, and many more. And this is now exactly the right segue to come to the main topic of the talk today, namely our synthetic wavelengths imaging research. So on a high level, what we do in this research track is we basically apply some optical and computational tricks to build a high precision interferometric time of flight camera. And then we use this time of flight camera for different applications in 3D vision or industrial inspection, but we also use it for fancier application areas, like, for example, imaging through scattering media at high resolution, or, for example, light in flight measurements. And these fancier application areas, this is what I will mostly focus on for today. So let's start. So most of you might remember from your optics class that if I image a rough surface with coherent light in an interferometer, then I get speckles where the phase map of these speckles is completely randomized. Yeah? And this prevents us now from calculating the object shape, because this time of flight information in the phase map of the speckles, this is now completely mixed up. Yeah? The solution to this problem is to go to larger wavelengths, which are larger than the surface roughness and then not subject to speckle anymore. But since it's actually pretty complicated to image and detect like millimeter waves, at least with high quality, people have started to use so-called time-of-flight cameras. And what these time-of-flight cameras are doing is they do a long wave modulation of the amplitude of an optical carrier. Yeah? The problem with these time-of-flight cameras is that the highest modulation frequency is typically limited by the time-of-flight hardware. And this means that the resolution of these time-of-flight cameras is not sufficient for many applications. So think, for example, about biomedical imaging applications, or think about like high-precision 3D metrology. And in order to solve this, people have started to do multi-wavelengths interferometry. So how does this work? So very easy. So you acquire a second field at a second wavelength, yeah? And then in our specific implementation of multi-wavelengths interferometry, you can actually show that by forming this correlation term here, yeah, you can see that these microscopic path length variations in the speckle fields, they cancel each other out, yeah? And then you get clear fringes on the order of a so-called synthetic wavelength capital lambda. And this synthetic wavelength capital lambda, this is basically the beat wave of these two optical fields. So that's also kind of an old hat, to be honest, but the new stuff and the fun stuff, this starts now if you start to look at the field properties of this beat wave, and if you start to treat this as a complex valued synthetic field. Because if you do this, then you can start doing computational optics with it. And this is exactly what we are doing. So to say it again from a slightly different angle, so what we do is we exploit frequency encoding, and we do this by overlapping two lasers with slightly different wavelengths. And this produces us a high frequency wave with a low frequency beat node. And then we can, after detection, computationally isolate this complex beat field. And this forms then our complex valued synthetic wave field at our lower frequency synthetic wave. So the important thing to say here is that this synthetic wavelength, capital lambda, is widely tunable, basically from microns to several meters. And this is because it only depends on the difference of the two optical wavelengths. The other thing that's pretty cool is that I can basically synthesize the same synthetic wavelengths in different carrier wave bands, again, because it's only dependent on the difference of the two optical wavelengths. And then the fact that the carrier of the information is in many cases still optical light, this allows me now to use fairly conventional detector architecture. So for most of the results that I will show you today, we use like ordinary CMOS detectors, like the ones in your mobile phone, for example. And the same way, this synthetic field is now immune to single scattering at rough surfaces. The same way, it's also largely immune to multiple scattering in scattering media. So here on the left side, you see a potential application in non-line of sight imaging. And then here on the right side, what you want to do is you want to look through scattering media, like tissue, for example, to see inner organs, yeah? Or another example here is long-range imaging through heavy turbulence or clouds. And as I have already discussed, in both scenarios, you have this problem that light is completely scattered, yeah? And the optical phases are completely scrambled. But in our case, we are still able to retrieve amplitude and phase information about the hidden object at this larger synthetic wave. And as soon as we have retrieved this information, one thing to reconstruct, or one possibility to reconstruct the object, is by doing computational optics, and in this case, performing holography at the synthetic wavelengths. So this means in particular that after I have captured these two completely scrambled optical fields, and I have calculated this correlation term that I have just described, then we can treat this now as a complex hologram of the hidden object at the synthetic wavelengths. And you can see here again the phase of this synthetic wavelengths hologram actually does show a clear structure and is not speckled. And now in order to reconstruct the object, we simply perform a numerical holographic backpropagation at the synthetic wavelengths, and by that we can reconstruct the object. So these are our results here from this original Nature Communications paper 5 years ago, where we imaged this U letter here through a ground glass diffuser, but also through a volumetric scattering phantom. And although they are like fairly old already, I still like to show these results because they nicely show that the synthetic wave actually behaves much like an optical wave. And what I mean by that is that the resolution gets better with decreasing synthetic wavelengths, yeah? But you also see that these measurements at smaller synthetic wavelengths or at stronger scattering, they are more susceptible to this degradation that you see here. And this degradation is basically synthetic speckle at the synthetic wavelengths. So this means there is like a certain trade-off space that can be spanned by this synthetic wavelengths imaging. And in our current and more recent work, what we do now is we try to exploit and further expand this trade-off space, all with this goal to push synthetic wavelengths imaging into novel application regimes. And of course, this comes with its own set of problems and challenges. And one challenge that is maybe immediately obvious to everybody here is the measurement of dynamic scenes. So think, for example, about living tissue or about moving fog or turbulence or something like that. So this is very hard if we want to capture these complex optical fields that make up the synthetic field, if we want to capture them in a sequential fashion, yeah? Because everything is moving. And this is exactly the reason why we have worked on motion-robust versions of synthetic wavelengths imaging, which I cannot discuss in detail here, but I give you the papers. So one thing that we did is we have developed a procedure to acquire the complete complex synthetic field in single shot, so only one camera image needed. And then in a more recent work that has just been accepted in Nature Communications, we use intensity correlations, and we actively exploit the movement of the scattering medium itself to synthesize the synthetic field in this case. And these motion-robust approaches that you see here, they now form the baseline for one of our more recent results here, where we do synthetic wavelengths imaging through dynamic dense fog. So in this measurement, we place this pyramid-shaped object behind a tank that is filled with very dense fog. And then in the camera image, we can see that we can absolutely not see anything about the object because the fog is so dense. But from these very faint off-axis cross-holography fringes that you see here, we can now demodulate both speckled optical fields, and from that we can synthesize the synthetic field. And the synthetic field now clearly shows this pyramid shape of the object through this very dense fog. And then in another very recent project, we do lensless fiber endoscopy with synthetic waves. So what you do here is you treat the fiber as a scattering medium. And then the gag here is that with our approach, you can even have a fair amount of scattering in between the fiber tip and the object that you want to measure, and it actually still works. And then at the same time, and this is also pretty cool, we exploit the scattering in the tissue or in the scatterer itself to expand the étendue of the imaging system. And by that, we can significantly increase the field of view of the fiber, which would be otherwise limited to this narrow numerical aperture of the fiber. So here on the right, you see this number 3 here that was imaged through the fiber plus an additional scattering layer of 5mm chicken breast. And you can see that the number 3 can still be reconstructed. Okay, so so in the last 5 minutes or so of my talk, I actually would like to talk a little bit more about the similarity of synthetic waves and optical waves. Because turns out if you generate now more synthetic fields from multiple optical fields and you overlap them, then you get, in complete analogy to optical fields, you get synthetic pulses, and these synthetic pulses can now precisely section your volume and can actually give you a much better longitudinal localization. And the cool thing is now that if we acquire this complete, or all these synthetic fields, then we have this complete complex synthetic pulse field in our computer, and we can freely manipulate it after it was captured. So one of the simplest things that we can do is we can turn the time knob in our synthetic pulse field, and then we can visualize how this synthetic pulse, which travels at the speed of light, we can visualize this at very high temporal resolution at different time instances. And of course, you can also visualize this as video, and this gives you so-called synthetic light in flight measurements. So this is a real measurement that you see here, no simulation. And although you can make now these extremely fast processes visible, yeah, You do not need a pulsed laser for this. You do not need a fast camera for this. You just need ordinary tunable CW lasers and a normal CMOS camera, like the one that you have in your mobile phone. This measurement here, this is such a synthetic pulse which is propagating through a strongly scattering medium with an embedded occluder here, and the light is entering from the left. And then in the video, you see how this photon horizon is propagating through this scattering medium and how it actually wraps around this occluder here. And then last but not least, this measurement shows a tightly collimated synthetic pulse, which is traveling through the medium and then is reflected by a mirror and changes direction. And important to say is, as I said before, since I have now the complete or all complete complex synthetic fields in my computer, I can freely manipulate the amplitude and phase of each synthetic field individually. And this allows me now to shape the synthetic pulse in time and space after acquisition. So for example, what I can do is I can shape the temporal pulse profile, for example, into a square wave here, or into a certain pulse sequence. Or another thing that I can do is I can do spatial pulse shaping. So for example, I can do this by computationally offsetting the different synthetic phases in each synthetic field. And by that, I can give the pulse, for example, the shape of a bunny. And then when I propagate this bunny-shaped pulse front towards the real bunny, then you see that the whole bunny surface is flashing up at the same timestamp. And now when I apply small defects on the surface, in this case they are so small so that you cannot even see them with your naked eye, and then basically hit the surface with defects, again with this bunny-shaped pulse front from before, then you see immediately these defects plopping up. So this is an example that has potential applications in industrial inspection or in medical imaging, for example. And that's basically it for today. So last but not least, I quickly would like to give you a short outlook where the journey goes here for this research track. So our team has been recently very fortunate to receive generous funding from AFOSR and NIH to indeed push synthetic wavelength imaging into novel application regimes. In particular, we have received a grant from AFOSR to explore synthetic waves in degraded visual environments. And we have received a grant from NIH of up to 2.6 million to explore synthetic waves for imaging of non-melanoma skin cancer. So very exciting times ahead for this project. And with this, I would like to conclude my talk for today. So if you now got interested in our research, please make sure to visit this website here or write me an email or find me during the coffee break. I should say we are always searching for strong collaborators. So if you have ideas how our research areas could complement each other, please don't hesitate to contact me. And this is the last thing I will say. I would quickly want to emphasize that my research professor, Murali Balaji, and my postdoc, Manuel Ballester, will be on the job market this year. Plus, my postdoc, Jiachang Wang, will start a faculty position in China next year and is also actively looking for collaborators. So if you encounter these three names, please be on the lookout and contact them. And that's it. Thank you very much for your attention.
Hi, thank you so much for such a great talk. Your method relies on constructive interference. So could you talk about either the coherence or noise requirements between the sources and any practical tips for getting it to work?
Yeah, so actually I kind of have glossed over this a little bit. So the condition that this method works is that the two optical speckle fields need to be correlated. So that's maybe something that not everybody knows. So when you have, when you have speckle and you change the wavelengths of the speckle or of your carrier, then the speckle fields start to change. And correlated means that the speckle field still needs to look similar for this, and this is the condition. So if you have stronger scattering, then the speckle field decorrelates faster. If you have not so strong scattering, the speckle field decorrelates slower when you change the wavelengths. And this in the end puts a limit on the smallest synthetic wavelengths that you can achieve. So this means for strong scattering, you need a fairly large synthetic wavelengths, and this influences also your resolution. So it's all a big trade-off space, But if you have a big trade-off space, this also means you can play a lot of computational tricks and other tricks by adding like additional modalities.
Thanks for the interesting talk. I have a question back up here.
Hi.
So you said that about generating synthetic pulse, right, for different media. So can we do this as adaptive feedback loop that, in the sense that if the media changes, we keep on changing the synthetic pulse so that we adapt to the change in whatever media that you are trying?
Exactly, yeah. That is actually something that we also actively following right now, yeah. And you can think about, interrogating the scene first with a rough pulse, if you want to say it like this, right? And then go finer and finer and finer, kind of like an foveated approach.
All right, one more question.
One more question.
What controls the, you showed the results of penetrating into scattering medium. What controls the how thick that you can image this through?
Yeah, so first of all, you need light, yeah? So if your optical carrier doesn't go through the scattering media, then you cannot have a synthetic wave, right? That is one criterion. The other thing is that the phase of the synthetic wave should not be scrambled. And in order to ensure this, you need a synthetic wavelength that is large enough. So this means if you go through stronger scattering media or thicker scattering media, then you need a larger synthetic wave. And this influences the resolution of your method. Thank you very much.
All right, thank you so much. Okay, our next talk is Professor Lei Qian from BU.
All right, thanks for the introduction. Thank you for the organizer for inviting me. It's always amazing for me to coming back to this community and appreciate the diversity and all the impact for computation imaging, computation photography can impact across all different diverse fields. So I'm going to switch in gear a little bit and talk about microscopy, specifically for phase imaging and reflection. For some of you know, my lab has been working on a lot of phase imaging problems. I thought for this talk I'm going to talk about something I have not talked about. Some new work we've been thinking about phase imaging in the reflection modes in the microscopic applications. Okay, so specifically I'm going to talk about how to think about phase imaging in the context of topography for 2D, then quickly switching gears and extend that for 3D problems. All right, to kick this off, I thought it might be instructive to think about and to explain what exactly phase imaging phase means in the reflection mode. So what you're looking at here is a reflective surface in blue. So the idea is that if you can shine light onto this reflective surface, so the idea is that the light will bounce back. So the typical idea, if you're sort of a physics optics background, the way to look at it is for well-defined so-called wavefront from a laser, for example, we'll have these well-defined planar wavefronts, which I marked there. And then as light bounces back, it will introduce this distortion of the wavefront. Hence, you have these purple distorted wavefronts. So the phase imaging, the holy grail of phase imaging essentially is trying to figure out how much distortion has been introduced by this reflected surface. Obviously, there are some assumptions underlying this diagram, which I'll come back later. But this is sort of the underlying assumption in geometry. I'm going to start off for this 2D imaging problems. And for this type of phase imaging problem, ignoring these scatterings and many other problems in the nanoscopic scales, this is sort of the typical topography problem. Okay, so the technique I'm going to talk about is known as Fourier tachography. There have been amazing talks yesterday talk about tachography. So Fourier tachography is sort of the Fourier deal of tachography. In a nutshell, what's happening is you can have imaging device that can control the illumination direction of your plane wave. So in the previous diagram, the light is coming from on top. This is one direction. But you can imagine you have a programmable light source that can introduce different k vectors or different illumination angles onto the sample. So now we're in a reflection, but nevertheless, as it turns out, if we take this simplistic view of 2D phase, we can still use the standard Fourier topography kind of view of seeing what the information is captured on the image. So specifically, what you're looking at are the Fourier space coverage. So basically, what you're seeing are is this rotating a circle that is the Fourier support of your imaging system. So our imaging system acts like, for microscopy, acts like a low-pass filter. So what you see is the support from this low-pass filter. And as you introduce different modulation frequencies due to different k vectors, so then you effectively capture different frequency band in the spatial domain. That's sort of how Fourier topography works. So we built this. So this is sort of the setup I'm going to use throughout this talk. So it consists of these LED arrays. As it turns out, in this lens scale we're looking at, LEDs provide sufficient spatial and temporal coherence requirement for this sort of phase measurement in the reflectance. So we need actually two LED arrays. One provides so-called bright field, meaning that the k vector is within the passband of your imaging system. The dark field simply means the carrier frequency is higher than the passband of your imaging system. So sort of you go through these sort of measurements, and the goal is, again, trying to figure out what is the topography. Basically means that what is the height map of the surface. Okay, so this is a slide just for those of you familiar with Fourier topography. It's a technique that can by reconstruction, after measuring all these images, the native image are low res, but after performing this sort of synthetic aperture type of space retrieval algorithm, you can achieve resolution that is several times higher than the native resolution of a microscope. But this talk is more dedicated on asking how accurate or how relevant of phase information can be reconstructed from this. The previous one is all sort of absorbance, amplitude information. So this is one of the sort of the resolution targets that we got from our collaborator from Samsung. So the benchmark measurement is from Zygo, which have slightly different mechanism, but it's sort of a benchmark of how accurate this height map we can get. On simple samples, it works pretty well. What's very interesting we find out in this work is that as we're approaching these structures that are relevant for semiconductor materials, specifically so-called high aspect ratio, meaning that if you look at the lines showing on these structures, they are very deep, but the opening relatively are small. So if you think about the ratio between the opening and the depths, this ratio, if it's larger, then it means it's harder for this sort of, because more complicated wave phenomenon kicks in, so it's harder to measure. And as a pleasant surprise, the method we are working on actually can outperform the commercial methods for this specific set of samples. All right, so hopefully that gives you some sort of idea of how 2D works. But the main talk here I wanted to talk about is how do we sort of think about these sort of problems in extending that to 2D, extend it to 3D. So we're coming back to the same diagram. So I wanted you to take a look at some of the assumptions we make. Specifically, if you think about a smooth surface like I draw here, clearly there are violations of the basic law of reflection because light are not supposed to go direct back. So what's happening is that basically you can argue if you make a staircase-like assumptions on these structures, perhaps this is still a reasonable assumption. And also you can argue sort of, if you recall the kind of structures I was showing before, we're kind of cheating because the kind of structure we acquire from our collaborator are staircase. Okay? But the question is how do we actually deal with more complex structures? Okay, so the solution we have been recently looking into is going back to even a more complex sort of optical process known as scattering theory. So for this audience, I thought I would just take a few slides. I was doing my graduate level imaging class and take a few slides just to get us back, introduce some fundamental geometries. We can quickly get us up to speed. So this is a standard scattering process. What you're seeing on these bubble-like things are known as scatters. So then what's happening is you have light coming from your left. The blue one, this is the input k vector. So then there are two dominant scattering information, which will be the main topic I'll talk about in the latter part of the talk. So the ones for the grain, these are going forward. So this is known as a forward scattering. And the arrows in red, these are bouncing back. These are light bouncing backwards. This is known as backward scattering. So I want you to pay attention to the fact that for forward scattering, if you think about the arrows or the k vectors, the green arrows are aligned with your incident k vector, whereas the red arrows, they have to make this U-turn. Okay? So this have tremendous implications of how you think about the information I encoded here and also how to interpret them. Okay, so putting that into the classical firstborn approximation, this is how we explain this in textbook. So you have these same arrows. As it turns out, if we take optical measurements, we cannot directly measure these vectors, but we can make differential measurement, meaning that our measurement is the difference, effectively the momentum we can measure, or the k vector measurement we can measure, is the difference between what is actually being scattered minus the incident. So that leads to this so-called evosphere being shifted downwards. So anyway, what you're gonna see later is that, so what this leads to is the central part where listed over here is the low frequency information. The reason is because the axis I'm showing you here, vertical axis is kz, so the axial spatial frequency. Horizontal axis is lateral frequency. For 3D imaging, as it turns out, the axial information is the key for a lot of the applications. So the fact that these spherical information, which are these sort of unit spheres telling us where the information is pointing at, the part that is closer to the origin is a low frequency, whereas the part that is further away from the origin is a high frequency. Okay, that's the explanation of what's happening. Not going to speed it up. So for diffraction tomography, it's sort of the gold standard technique for doing this sort of 3D scattering measurement. So there are sort of different ideas. For the transmission mode, what you do is you scan these illumination angles, and you have detectors that behind the sample. So this is so-called transmission measurement. Because it's sort of geometry, naturally you can only capture the forward scattering information. Whereas in standard backscattering sort of diffraction tomography, what you do is just use the same geometry, you put the detector behind the sample, same way as your illuminated sample, same side. So you only capture the backscattering information. Because I mentioned that our funder was from Samsung, they are particularly interested in stuff that are sitting on a reflected surface, like a silicon. So we thought, why don't we think about applications where we shine the light through the sample, but then we also in the presence of a strong reflective surface, and capture the information from the same side of the illumination by the detector. As it turns out, if you look at the Fourier coverage, we can actually, using this geometry, to harvest both the forward scattering and backscattering. If you want to take anything from this talk, this would be the main point. Okay, so I'm gonna walk through some of the more details of this, hopefully just to tell you more insight. So what's happening is you have the incident, you have this forward scattering and back scattering from this incident. So then there's a complementary process because you have a strong reflector. The incident light will be bounced by the mirror, think about it as a mirror, which itself will generate its own forward and backward scattering. And all of this will kind of, if you think about this as going to the right direction, it will be eventually making back due to the presence of reflector. Okay, all in all, your measurements will capture these 4 different components of forward scattering and back scattering. And putting all of this together, and there's this sort of short version of all of this, but hopefully you believe me that all of these 4 components actually contains slightly different information that can be better explained in Fourier space, which are these arcs I'm showing you here. And recall that the main thing I tried to review was the lower part of the spatial frequency along axial direction was forward scattering, whereas the further part high frequency information was backscattering. So all of these, you can derive this using a firstborn approximation. I will spare the math behind it. Just to say that, as it turns out, even though the scattering process is very complicated, but if you make some reasonable assumptions and linearize the problem, you can actually formulate it as a linear problem. And this is sort of the visualization of what you get from these sort of linear measurements. So the difficulty is that, remember, all of these are all being captured on your detector all at once. So it's a linear superposition of all these components. The question is, how do you disentangle that? And what is the requirement of this? This is sort of a different visualization of this. As it turns out, I think there was a talk this morning talking about state space. I can definitely relate to some of the insight we got from this paper. As it turns out, this mixture is at per pixel. So even though it's a very messy problem, each time we take a 2D measurement, but this linear system is actually, superposition can be performed per pixel. So we actually solve a regularized least squares problem, pixel by pixel. So then you formulate then you form the final reconstruction. So that's sort of more detail how we do this. It's interesting to look at microscopically what this means. Okay, so I'm going to show you this simulation just to illustrate the point. Okay, so in microscopy, one of the things is that different objects may have different properties. Some of the objects are transparent. We call it phase object. It basically only introduces sort of the phase delay I was illustrating. Some are absorbic objects, which basically means it only introduces reduction of the intensity. So this is a fake object. At the bottom are purely phase, and on the top are purely absorptive. And also these round objects, I call them solid structures, whereas these arc kind of interface, these are interface. Okay, so this is just illustrate they have different spatial frequency information along Z. Okay, so once we reconstruct this, we can easily decompose the reconstruct information into 4 scattering parts. So the forward scattering part, because it occupies the low frequency information along Z, so you can see that originally they have these spheres. So then they have this mild elongation. This has to do with the support we got from the reconstruction. But you can hardly see the interface from the reconstruction. So this is not because of display, because it's actually not present. So the interface, because if you think about the Fourier information of this interface, it has a very strong axial variations, but very mild lateral spatial informations. So they're only present in the axial backscattering information. So this is sort of the key insight of why do we bother to harvest this backscattering information. Okay, just to show this actually works, I'm going to skip some of these. One of the fun applications we looked at was sort of imaging through scatters in the microscopy application. So we have these occluders from tissue papers. Underneath is this phase object with a resolution target. So the benefit of doing this, all in all in this application, was allow us to quantitatively image through these complex objects and still recovering high resolution information. As a microscopy application, we also apply this for imaging cells. So the punchline here is to show you that Fs means forward scattering. Because these are low frequency information, they're primarily sensitive to the internal structures of cells, whereas backscattering, because they're more sensitive to interfacial information, they're more sensitive to the membrane of the cells. Okay, to sum up, I talked about reflection phase imaging. Hopefully the main takeaway is that depending on how you interpret the data, how you think about the phase information are being captured. You can either think about them as a 2D reflectance surface, but more complex structures deserve more thought on the underlying 3D process. With that, thank you for your attention.
All right, I'm curious how this compares to like how OCT thinks about, like OCT is also measuring reflectance from different layers, but I think it's a different physical quantity that they're displaying.
Yeah, so we're out of time, so I skipped this. So in OCT, as it turns out, because of the way they measure the phase, they're missing the conjugate part, the bottom part of the sphere. Because of Fourier properties, if you don't have the bottom part, you cannot tell whether it's a phase reflectance or absorbance reflectance.
All right. Let's thank Leah again, and we can get our next speaker up. So that was our 2 invited speakers, and now we will have 3 contributed talks. All on holography and coherent optics. So the first is, I assume, Jacqueline Yang from Stanford.
Okay, hi, I'm Jackie. I'm a second-year PhD student at Stanford in the Physical and Spatial Intelligence Lab, and I'll be presenting our work on mutual intensity factorization for computer-generated holography. This is joint work with my collaborators Brian, Sungwoo, Sion, and Gordon. So in recent years, holographic near-eye displays have unlocked breakthroughs in the design of spatial computing systems. For example, the use of holograms has enabled novel, ultra-compact AR and VR glass designs. Additionally, these displays have been used to produce unprecedented 3D image quality with virtual content that accurately reproduces the focus cues that would be seen by the real world. So before we get into the method, I'll first review the holographic principle. In this system, we shine a laser through a collimating lens and use a spatial light modulator, or SLM, to control the light distribution within a target 3D volume. What we need to do here is to find the right SLM pattern, which is at the core of holographic displays. So to solve this problem, we have a class of algorithms called computer-generated holography, or CGH. And in essence, we treat what's happening in the display system as a computational light transport problem in wave optics. And these algorithms calculate the pattern we need to display to achieve our desired target content. In computer-generated holography, we typically have a reconstruction algorithm that converts a 3D scene to some target representation. So these can be a bunch of different things, ranging from geometric primitives, so things like meshes, point clouds, and Gaussians, to image-based representations, so things like light fields, focal stacks, or synthetic apertures. And finally, we design an algorithm that converts these representations to a complex wavefront or a phase pattern that can be displayed on a holographic display. So this is often referred to as the encoding step for the SLM. In computer-generated holography, many display systems use time multiplexing to improve image quality. And this is the process of rapidly displaying multiple random phase holograms where each frame produces a different speckle pattern, and then averaging them over time to reduce speckle while preserving desired scene properties. I'll now introduce the concept of mutual intensity, which is a correlation function from statistical optics that describes the pairwise interference of the optical field with itself via an outer product. And essentially, this function tells us how correlated the wavefront is at any 2 points in space. So this figure here depicting mutual intensity is from a 2014 Optica paper, and I'd like to use it to highlight some properties of the matrix. So first, the mutual intensity matrix is always Hermitian, meaning the correlation is symmetric. It's symmetric across the diagonal up to complex conjugation. And visually, what this means is that on the diagonal, we have the intensity, so these values are going to be real and greater than or equal to 0. Off the diagonal, the values will be symmetric in magnitude with a phase flip in sign across the diagonal. And in addition, the eigenvectors represent the coherent mode. So this is from the coherent mode decomposition. And this is important since practical scenes often have rapidly decaying eigenspectra. So this allows us to use mutual intensity for accurate low-rank approximations of a scene. The use of mutual intensity in holography is a theoretical contribution that unifies existing methods. And these mathematical properties are what lead us to our approach, which is to factorize the hologram into a few frames by solving this optimization problem where at each iteration, we compute the loss over the mutual intensity of our learned complex field. So with so many possible representations for computer-generated holography, a natural question arises, which is which representation is actually best suited for our use case? And this is an important question since different scene representations yield different formulations of the optimization problem. So to answer this question, we'll focus first on intensity-based representations. And we want our representation to satisfy two main criteria. So first, it needs to be good, meaning that it produces very high image quality. And second, we also need it to generalize well over many different viewpoints. So when we consider these intensity-based methods, the difference in performance is often closely tied to what the optimization target is. So going through common intensity-based methods, we have focal stack optimization, which is when we have a set of depths where we try to reconstruct the correct intensity at each depth plane when focused there. So in this case, the loss is defined in terms of focal images, which are angular integrals that collapse the pupil. In this case, view-dependent shading and reflections may not be correct, and we don't learn intermediate depths well. In light field optimization, we build a light field and optimize over the radiance of each tile or view in the light field grid. Here, radiance is the amount of light traveling in a specific direction at a specific point in space. And in this case, we have a spatio-angular resolution trade-off, and we also don't learn the intermediate views in the grid very well. Synthetic aperture holography is, I guess, the most modern of these methods. We have a hologram where we stochastically sample a different pupil or aperture at each iteration in the Fourier domain. In this case, we can think of it as applying a Fourier filter that will select a certain view or sub-aperture at each iteration. And these produce very high-quality holograms, but we end up being limited by the number of sub-apertures we can use, where we need many masks for uniform sampling in frequency space. And then finally, this brings us to mutual intensity factorization, which is our method. And this method is not optimized based on intensity images at specific viewpoints, but rather it captures the full structure of the wavefront, and thus it's able to reconstruct well at all depths and all angular views. So to better describe mutual intensity factorization, I'll sort of walk us through our method pipeline. We start out with a set of M, which is some very large number of random phase frames that when multiplexed produces a high quality hologram. We then compute the target mutual intensity from these frames, which I'll call U. And we learn a reduced set of patterns corresponding to a reconstructed wavefront that solves our mutual intensity optimization problem. We then display the reduced set of patterns T, where T is ideally far less than M, on the holographic display to reconstruct the target scene. And in this case, requiring fewer time multiplexed holograms helps make the representation compatible with the limited refresh rate of modern SLMs. So before I show the results of our method on real scenes, I'd like to walk us through a simple experiment illustrating the properties of image-based methods that are traditionally used to create perceptually accurate holograms. So this is the classical double-slit experiment, which highlights a fundamental limitation of supervising holograms using only a finite number of image measurements. In this figure, we show simulated results of the double-slit experiment where we have 2 point sources propagated a small distance along the optical axis using the angular spectrum method. And here we're looking at the propagated intensity patterns. So in this example, we optimize holograms using focal stack, light field, and mutual intensity supervision, where in these methods, focal stacks and light fields involve sampling at a finite set of views. So this would be the number of depth planes used for focal stacks, and then the number of horizontal and vertical views in the grid for light fields. And the benefit of mutual intensity here is the additional freedom afforded by the view-agnostic nature of the optimization procedure. So looking at the results of the propagated intensities resulting from each type of intensity-based supervision, we can evaluate the reconstructed intensity over many different propagation distances. And the goal here is not to compare optimization procedures, but rather to compare the information that's available to each representation. So here we see that when we optimize with only a few views, while focal stack and light field supervision match the sampled views reasonably well, they end up being constrained by the finite measurement budget. And so these measurements do not uniquely determine the underlying mutual intensity. So multiple wave fields can be consistent with the same supervision signal. And as a result, the reconstructed interference pattern degrades between the sampled planes and in some cases even loses the expected symmetry. So I'll return to this point later, but the key idea here is that focal stacks and light fields are measurements derived from the underlying mutual intensity. And with a finite number of measurements, multiple different mutual intensities can produce the same focal stack or light field observations, which leaves the inverse problem underconstrained. We can also explain this idea mathematically. So mutual intensity can be thought of as equivalent in information content to the Wigner distribution, meaning it contains exactly the same information, just expressed in a different coordinate system. So here we can see that mutual intensity and the Wigner distribution function can be thought of as a Fourier pair, where we just sort of do the Fourier transform of the mutual intensity expressed in these difference coordinates. And prior work by Zhang and Lavoie from an ICCP paper in 2009 actually has shown that the observable light field can be thought of as an aperture-filtered or phase-space blurred version of the Wigner distribution, which we've shown is equivalent from an information standpoint to mutual intensity, encompassing more information than light fields in the wave optics regime, which is always the case in holography. Focal stacks can also be thought of as obtained from light fields by integrating that light field over all viewing angles. And so this gives us a hierarchy of representations in terms of information content, with mutual intensity at the top, and then light fields, and then finally focal stacks. So in other words, focal stacks and light fields are derived measurements of mutual intensity rather than equivalent representations. So we have information loss. So I'll sort of now walk us through the implementation of the method. And from an information standpoint, it seems that optimizing mutual intensity should be the obvious choice. But there's a catch, which is that at high resolution, so for example, if we have a modern SLM with a resolution of 1920 by 1080 pixels, the mutual intensity matrix is 34 terabytes, which is more than 4 times 10 to the 12 pixels in complex 64 precision. And this ends up being prohibitively large. So to solve this issue, we implement a blockwise gradient accumulation strategy where we randomly sample all blocks in a batch and then accumulate the gradients once per epoch. We also take advantage of the mathematical symmetry of the matrix, and we efficiently load from memory to reduce the computational load. We then construct a benchtop holographic display prototype to validate our method in hardware. So this is just the classical setup with a laser, a collimation lens, SLM, a 4F system, and a sensor, which in this case is an RGB camera. And we mount the Fourier filter and the camera on translation stages for our captures. And I'll now show some results of mutual intensity factorization where we optimize a complex wavefront using our method, and then we use these wavefronts to reconstruct focal stacks. So we validate our method in simulation on the left and in hardware on the right, where we demonstrate that focal stacks are able to maintain correct defocus behavior, so the ability to focus at different depths like the front and the rear of a scene. I'll also show some simulated and captured results of mutual intensity factorization on light fields. So again, we reconstruct these complex wavefronts and then use them to generate light fields, and we show that our method maintains accurate parallax. So we can see the left view, the right view, as well as an epipolar crop with a slant line showing movement as we move from the left view at the bottom of the crop to the right view at the top of the crop. And then finally, we would also like to emphasize that mutual intensity can be thought of as a generalizable or apparent representation of alternative intensity-based methods. And in the paper, we prove this mathematically, that these objectives can be expressed in terms of the mutual intensity residual, which is this delta J term, by applying derivable linear transforms to the left and to the right of the residual. So we can see here that we're able to rewrite the loss functions of existing intensity-based methods, so focal stacks, light fields, and synthetic apertures, in terms of the transformed mutual intensity residual. And the full derivations of these transforms are included in the paper, but we show the key equations here. And the key point here is that mutual intensity provides a unifying optimization framework that encompasses multiple different holographic objectives. So to conclude this talk, I'd like to leave with one central idea, which is the idea that mutual intensity is a physically principled representation and optimization objective that can be used in computer-generated holography, and it preserves wave information while subsuming existing image-based approaches. So I'd like to thank the Stanford Physical and Spatial Intelligence Lab, the CAVE Lab for hosting me, and also all the following fellowships that made this work possible. Thank you.
Questions? I feel like I missed a little bit of what's going on, but you used mutual intensity capture wave effects. So like light field doesn't for sure, it's ray optics, but focal stack can capture wave effects if you like use it properly. And then your example had like double slit, which is really one coherent mode. So like if you like use more coherent modes, does the mutual intensity start to break down?
I think it should be able to represent it, but that was just a toy example that we used for just trying to show one specific case where mutual intensity can capture something that the other methods don't. Sorry, what do you mean? What do you mean by that?
Well, I'm just asking for the definition of this mutual intensity. You look at the correlation in two intensities, right? Two fields.
Yes.
Two fields. But you do the average over something to get to
Oh, we do the average over the number of frames that we're using for the time multiplexing, because typically we use like a collection of many different fields. Thank you for your question.
All right, thank you very much. Let's thank the speaker again. All right, our next talk is a contributed talk, Pancake Multi-Source Holography, and it's from CMU by Sagnik Ghosh.
Hi, I'm going to present Pancake Multi-Source Holography, which is a compact high Itando holographic display that breaks the memory effect using a single reflective phase SLM. This was a joint work with my collaborators, Praneeth and Ashwin. So yeah, to get started, some of the most capable holographic displays use multiple spatial light modulators or SLMs that to do things that one SLM simply can't do. For example, removing noise or expanding the field of view. But as impressive as these designs are, they are initially conceived on paper using transmissive SLMs. But the SLMs that the high quality SLMs that you'd really want to use are reflective in nature. And stacking multiple reflective SLMs blows up the size of the system. But our key insight is this: the reflective nature isn't really the problem, it's actually the solution. Because a reflective SLM bounces light back, we can simply route that light back onto the same SLM so that one physical SLM does the job of two different SLMs. And the very property that made these designs bulky is exactly what lets us fold it into one. And what you get at the end of the day is a compact display with the power of a multi-SLM system, but it's built with just a single reflective SLM. I will get to how all of this is implemented in just a bit, but I'll first talk about why multiple SLMs were needed in the first place by existing designs. Let me first do a quick introduction to holographic displays. And to those of you who were at Grace's excellent introduction to holographic displays yesterday, this should seem pretty familiar. And this is just a condensed version of that. So the simplest holographic display that you can think of is it really just starts with a single point source of light. And then it's followed by a lens which collimates the point source of light into a clean collimated plane wave. And then the SLM is what shapes it into a scene that you actually want the viewer to see. There are two main quantities that we care about. The first is the eye box extent, and that is simply defined as the small region within which your eye needs to be to actually see the projected scene. And in this simple setup, it's simply the physical extent of the SLM. The second quantity that we really care about is the field of view, and that's simply how wide the scene looks to the viewer. And the étendue is defined as the product of these two quantities, eye box and field of view. And this is the important bit. It can be shown that for a simple display like this, the étendue is capped by the number of pixels on the SLM. And simply increasing the number of pixels on the SLM is not a scalable solution. So the next natural question is, can you get around some other way to expand the Itando? And a well-known way is to just add multiple sources instead of just having a single source. But here's what happens when you move a single source on its own. The scene doesn't really change, it just shifts. And when you add a whole array of sources, all you get are multiple copies of the same scene. So you do technically increase the field of view, but you don't have unique content across the entire field of view. And that's exactly what's called as memory effect, and it's what any multi-source design has to defeat. The standard fix is to add a second modulation plane. I think Grace talked about that in her talk in a slightly different context. And so it's basically a second SLM whose job is to decorrelate the light from the different sources. And it works because the input sources are spatially shifted. So the wavefronts associated with each of the sources land on different local regions of the second SLM. And that's what decorrelates them. And those copies finally merge into one clean image across the entire field of view. As we have already seen, a lot of strong prior work is built on exactly this two-stage idea. But these are bulky 2 SLM systems. And as I've already mentioned before, it only gets worse once you try accommodating reflective SLMs within these designs. But here's the main motivation behind our work. What you fundamentally need is 2 modulation planes and not 2 separate SLMs. And that begs the question, can you get away with just a single SLM? Can a single SLM provide more than 1 modulation plane? And that is exactly what we do in our proposed design. We borrow ideas from pancake optics. It's the polarization-based optical folding that is typically used to make VR headsets thin. So here's the design. The main idea is to bounce the light back and forth between a reflective polarizer and the SLM, and so it lands on the SLM more than once. The input light is linearly polarized, and the quarter wave plate makes it circularly polarized. And what you need to remember is that circularly polarized light always flips handedness when it reflects. And in this particular design, while it flips handedness, it also gets modulated by the SLM. And that's our first modulation plane. And on the way back, the quarter wave plate turns that flipped light into the orthogonal polarization, and that's why the reflective polarizer reflects the light back instead of letting it through. So it heads to the SLM a second time, gets modulated a second time, and then back out to the eye. And that's how we get 2 modulation planes from a single SLM, which is what breaks the memory effect. The one catch, if you haven't noticed already, is that both the modulation planes or both the modulation passes have to share the same phase pattern. But as we'll see in results, that costs surprisingly little. Let's look at how our method stacks up against prior Itando expansion methods. Ko et al. And Zhou et al. Pair a single SLM with a static mask, and we clearly outperform the static mask methods. The closest to our design is Chow et al.'s dynamic Fourier modulation, and as you can see, the numbers of our design are in the same ballpark despite half the degrees of freedom because we use a single SLM instead of 2 SLMs. And that's really the key point. We inherit all the benefits of 2-stage dynamic Fourier modulation with just a single reflective SLM. These are simulated focus cues. Visually, our method is pretty hard to tell apart from Chow et al.'s dynamic Fourier modulation. The metrics are somewhat worse, but again, that's with half the degrees of freedom since both our passes share the same phase pattern. Parallax pretty much tells the same story. We stay right on par with dynamic Fourier modulation, and that's with half the degrees of freedom. We also build a hardware prototype to validate all of this in practice. What you see in this picture is a bunch of components that we've already walked through. And I think anyone in this room or otherwise who has ever tried building a holographic display would probably relate to how annoying it is to actually get it to work and actually calibrate the display. And my advisor can attest to how miserable it made me for a while. And that's exactly why I want to talk about some of the hairy details that goes into calibrating a system like this. So we start with optimizing the entire system in simulation. We start with the source plane, and then we go to the first modulation plane, and then to the second modulation plane, and then all the way to the retina. And we do all of this in PyTorch, so it's differentiable. And we can solve for the phase pattern that best reproduces whatever scene we want the viewer to see. The main idea is to model all the non-idealities that you can think of or you observe in the system. The plane waves incident on, so first of all, the plane waves that are incident on the SLM at the first pass aren't perfectly collimated. So we allow for a smooth phase calibration term measured directly off the prototype. And we keep those correction terms frozen during content optimization. The individual source wavefronts incident on the SLM at the second modulation plane are warped geometrically due to optical aberrations in the system too. And that is why we allow for an additional geometric warp correction term per source, which we also measure directly off the prototype. The calibrated phase aberrations that I mentioned earlier and the calibrated per source geometric warps are incorporated carefully into the content optimization loop. And that's so the phase pattern we end up with is it actually matches the real optics and not just some idealized version. Depending on what we are after, we can either supervise the optimization on focal stack scenes, which gives us defocus cues, or on light field views, which gives us correct parallax. And I think the next couple of slides perfectly encapsulate why it's so hard to calibrate the system. So if the two modulation passes are perfectly aligned, the reconstruction is pretty clean, it's crisp. And if you just shift the second modulation pass by just a quarter of an SLM pixel, which I think is about 2 point something microns, you can see the contrast start to drop already. And if you shift it by half an SLM pixel, the image is barely visible. And if you shift it by a full SLM pixel, it disappears almost completely. And yeah, that's the main problem. And to mitigate this, we do add random subpixel shifts at every optimization iteration to make it slightly more robust. But to be honest, it only works to a certain extent, and it's still pretty sensitive. But despite these challenges, we do, as you can see in one of the captured focal stack scenes, you do get pretty decent defocus cues, although at a slightly lower contrast. To give you some more context, this is about an 11 by 11 degrees field of view and 6 by 6 millimeters eye box. And here's a second captured scene with similar specifications. And the whole reason you moved from a single source to a multi-source array was to get a bigger eye box and undo. And you can clearly see the expansion in eye box and the experimentally captured eye box using our setup. At the periphery of the eye box, the single source image almost completely vanishes, while the multi-source version still reconstructs an image. As you move towards the center, even the single source starts to come back. And at the periphery, again, the single source version falls apart. And if you flip between the viewpoints, you can see view-dependent effects in the multi-source case. So to wrap up, a single reflective SLM gives us 2 modulation passes. And keeping the 2 planes distinct is what breaks the memory effect, and sharing one pattern costs very little. And our prototype reaches a 9.3 times larger eye box in undo with real defocus and parallax. The main limitations are subpixel alignment, some polarization leakage due to the components we use, and having to use a 4-bit SLM for its polarization agnostic nature. Thank you. happy to take questions.
And I understand those pancake lens full of aberrations. So my question is, how do you take into account the aberrations of your lens, of the lens, your objective lens, in your simulations of holograms? And if you take into account, how do you take into account? Because you know that the Zernike polynomial is a function of field.
So we do take into account lens aberrations, but not explicitly, more implicitly, because the lens aberrations manifest as smooth. It just blurs out the pattern that we want at the second modulation plane. So you can sort of adjust. You can adjust for like a smooth phase correction term, which is what I talked about, to account for that. That's basically what we do. We assume in all our simulation results, we do assume an ideal lens, but to actually get the results, the experimentally captured results that you saw, we had to account for lens aberrations and stuff like that.
All right, Grace.
So you're getting, you say 9.3x expansion here.
Yeah.
What limits the amount of expansion you can get with this sort of approach?
So we use a 4x4 array, so you'd think we'd get closer to a 16x expansion. But the extent of the physical extent of the SLM that we use, it limits the extent of the eye box. And so what we end up doing is having overlapping spectra of the individual sources at the second modulation plane, and that's sort of what caps the eye box. I could imagine maybe using a different focal length to get a higher, I guess you use a shorter focal length between the two modulation passes, you'd get an even higher étendue. Also, maybe a larger SLM. That's what I can think of.
Thanks.
All right, maybe one last question while we're setting up the next speaker.
Hi, I had a question about, so you fold the image by like bouncing off the SLM and then bouncing off the SLM again. So what if you do it like, a pancake stack that's like in your dreams where you have like a million of them? So could you keep bouncing it off and getting better and better effects by stacking SLMs? Like I know it's hard to calibrate and this sucks.
Yeah.
But
yeah. So that's a really interesting question, because that's kind of the idea we started off with, and it wasn't even a pancake design. It was more we internally called it infinite bounce holography. It was we just used a half mirror, and a portion of the light leaks out at every bounce, and that's. If you actually do the math, it doesn't work out even in simulation. You sort of get this weird vignetting thing where the energy just is mostly concentrated at the center.
cool. Thank you.
Yeah.
All right, thanks to speaker one last time. All right. Our last talk before lunch is Esther Lin from Toronto.
All right, so the diffraction limit is a fundamental limit on resolution for all optical systems. And today, I'll talk to you about a new approach for imaging beyond it using optimized superoscillatory point square functions. The diffraction limit arises from the fact that all imaging systems have a pupil, which is the opening through which light passes through when it enters the optical system. Because this pupil can't be infinite in size, the image of a point source is always a blurry 2D pattern called the point square function, even if the optics is perfect. This PSF, or point square function, is given by the Fourier transform of the pupil, and for a circular pupil of diameter d, the diffraction limit is defined as the width of this bright central spot. So this spot, this central 0 to 0 distance, is called the Airy disk, and it's completely determined by the wavelength of light and the diameter or numerical aperture of the pupil. And this central lobe describes exactly how the image of a point source is spread out. So the narrower this lobe, the less spread out the image will be, and the system will have better resolution. And according to the expression for the diffraction limit, the only way to reduce the width of the central lobe for a given wavelength is to increase the pupil diameter. So despite what the diffraction limit might suggest, it turns out that there is a way to design optical systems whose Poinsot function has a narrower central lobe while keeping wavelength and pupil diameter constant. The key is a mathematical principle called superoscillations. It's been known for decades that one can define a function that fluctuates faster than its highest frequency component, not globally, but in some local region of the domain. And this principle has been used to design Poinsot functions as well, where an SOPSF has a central lobe that's narrower than the diffraction limit. Let's zoom out a bit out of the subdiffraction central lobe and look at the three main characteristics of an SOPSF. It has that central lobe, whose width is below the diffraction limit, potentially many other side lobes with similar magnitudes and widths, and distant sidebands whose width is above the diffraction limit and whose magnitude is potentially much, much more than the central lobe. And as we can see here, the subdiffraction features are local, and they fall in what we refer to as the superoscillatory region of the PSF. So a superoscillatory PSF can be realized by engineering the pupil. We keep the pupil diameter fixed and modulate the pupil function. Compared to other subdiffraction imaging methods, superoscillatory imaging does not depend on sample labeling, in contrast to fluorescent microscopy methods. It's single shot to achieve subdiffraction resolution, in contrast to phototychography. And it works in the far field, in contrast to near field microscopy. So overall, SO imaging has been shown to achieve passive subdiffraction resolutions with PSF engineering. But although some families of SO functions have been explored, no general method for constructing them exists, and the limitations of SO imaging is still poorly understood. There are two main branches of prior SO-PSF design methods. The first uses correlate spheroidal wave functions. These are band-limited functions optimized for spatial concentration. However, these formulations don't explicitly guarantee superoscillatory lobes. The second is based on superdirective antenna design. These methods create narrow antenna beams, which optical SO designs have adapted to produce narrow central lobes. However, they are formulated for discrete antenna arrays rather than filled aperture optical systems. Neither of them provide insights into how general SO functions can be designed or optimized, and they have been tested on sparse binary objects. So in summary, our contributions include the first explicit construction rule for general SO functions, where SO behavior is guaranteed with explicit control over zero crossings. Solutions are physically realizable in optics, and we characterize the space of SO functions. Next, our construction rule can be used for differentiable optimization to explore the space of SO-PSFs, where any loss can be incorporated and we directly optimize for reconstruction quality. Finally, using our optimized SO-PSFs, we can get resolution improvements 1.3 to 3 times under the diffraction limit, and we also investigate the limitations of SO imaging. For the rest of the talk, I'll start by going over the theory of constructing SO-PSFs with an intuitive 1D example of SO functions, moving on to a product-based construction and a sum-based construction in 1D, and the space of optically realizable 2D PSFs. Now, let's start by using simple 1D construction to show how a function can oscillate faster than its highest frequency component. The goal is to construct a lower frequency function that's superoscillatory, matching 8 Hz in the local region here. First, we notice that there are 3 zeros in this region, which is one period of 8 Hz. We can take a 1 Hz sine and see that it crosses one of these zeros. We can take another sine, shift it, and it'll cross another zero, and another. And if we multiply them all together, we get a function that crosses all 3 zeros. It locally fluctuates like an 8 Hz sinusoid, despite being band limited to 3 Hz. Now let's generalize the example into a product-based construction. First, we choose n desired zero locations. Then we have m low-frequency basis functions and shift them to enforce these zeros. The product's band limit will be the sum of the component frequencies. Finally, the SO function is obtained by multiplying the shifted basis functions together. However, any product of sinusoids can be rewritten as a sum or superposition of sinusoids. This shows that the product construction is only one solution within a broader space of superpositions, motivating our next construction. Let's once again choose n zero locations, then choose m low-frequency basis functions, where now the largest basis frequency is the construction's band limit. Finally, we solve for coefficient c so that the sum equals 0 at all desired zero locations. In terms of degrees of freedom, we have n zero locations, m coefficients, and m basis frequencies. To extend the construction to rotationally symmetric optical systems, we replace 1D sinusoids with a rotationally symmetric 2D basis. A circular pupil gives rise to a spatial function whose cross-section is a jink, and thus we'll use jinks as our basis. To generate an SO region, we constructively and destructively interfere different sized pupils, and thus we get to express our SO pupil as a superposition of jinks. So in all, an SOPSF's degrees of freedom are the width of the SO region, number of zeros in the SO region, number of coefficients, and the number of frequencies. For m much larger than n, we have a big solution space that can be explored through our upcoming differentiable optimization. Okay, now let's proceed with the differentiable optimization to explore the space of SOPSFs. In this work, our SOPSF has two sets of learnable parameters, the zero locations and the jink coefficients. We initialize with the minimum norm solution, and for easy optimization, we set the basis frequencies to uniformly sample the pupil diameter, and we also pre-explore discrete variables like the SO region width and the number of zeros with a grid search. And this will give us an SO pupil, which we can use to simulate the incoherent measurement captured by an optical system. We can reconstruct the object using linear deconvolution, and then compute a loss by comparing the reconstruction to the ground truth object. The loss combines both mean squared error and structural similarity computed on the reconstruction and on the first two levels of the Laplacian pyramid. We optimize the loop with gradient descent. Now let's take a look at our simulated results. Performance depends strongly on object structure, particularly sparsity. Here we test objects whose features are spaced 1/3 the Airy disk apart. We find that the diffraction-limited image can't resolve the objects, while the raw SO image already has more details. After Wiener deconvolution, the diffraction-limited image remains unresolved, while the reconstructed SO image recovers the objects. The learned SO pupil and PSF are as shown. Next, we evaluate on denser objects. Here we show a Siemens star and a binary band-limited structure noise pattern. Here are the raw images and the reconstructions. And we see that our learned SOPSF produces the best resolutions. Our SOPSF generalizes to dense grayscale objects. Here we show text and a cat image. Here are the raw images and the reconstructions. And again, our learned SOPSF produces the best reconstructions. Next, let's assess the limits of SO imaging. The SO region in SOPSFs is very low energy compared to the sidebands. And this raises the question, how do resolution improvements change with the size of what we're imaging and noise? First, SO performance degrades as object size increases. We vary object size and compare diffraction-limited SO reconstructions using image metrics, and we find that even with retraining at each size, SO performance still degrades at larger object sizes. Therefore, SO imaging is best suited for small objects within the SO region. Second, SO performance is best with low read noise and high photon counts. So far, all results are in simulation. The next step is for me to go build a setup. But however, for decades, super oscillations have largely existed as a mathematical curiosity. Our construction rules turn it into a controllable design space for optical systems. And we introduced the first differentiable framework for optimizing SOPSFs directly for image quality, which opens up a broader design space for downstream imaging tasks. And finally, we also use it to highlight key factors limiting SO performance. Thanks for your attention.
Hi, thank you.
Hi.
Can you give us a flavor of how you plan on like making the actual lens, please?
Yeah, I think the first approach that I might have a little bit of experience with is a phase SLM, where you can do super pixeling to get the coefficients to have both positive and negative sign. That might be a first place to start, but the previous talk actually had some pretty interesting optical setups that I might need to think about a little bit and see if we can incorporate here as well. Thanks.
Hi. Over here. Hi. Thank you so much for the talk. It was really clear, and I think I learned a lot about this idea of SO imaging. Hi. So I just wanted to ask, you just briefly mentioned in the background some application or comparison with fluorescence imaging, and you wouldn't need any sampling labels. Can you just clarify or just expand a little bit more on that with SO imaging, that you wouldn't need those labels?
Yeah. So with SO imaging, all you're doing is you're changing the Poinstar function. So you're changing the optical setup, whereas in fluorescent microscopy, you have to pre-treat your sample with fluorescence. So you're touching the sample side, where we're changing the optic side here.
I see. So just changing the optics, and you're able to then localize this. Okay.
Exactly.
Awesome. Thank you.
So what kind of factors determine how difficult such a PSF would be to manufacture? And can you write them into the optimization problem?
Yeah, so I think some of the common ones would be discretization and how fine the pupil has to be. We have simulations in the paper saying that it's actually not that hard. So you need 8-bit quantization, and the spatial discretization on the pupil is not that strict of a requirement, actually. So all that's left is I have to just go build it. Thanks.
All right, thanks very much.